Welcome back, everyone. Thanks again, Mandy, for the wonderful talk on spatial models. It's really interesting. And really nice way to incorporate spatial information, right? That we leave on the table if we do standard analysis. I'm going to talk about standard analyses. And why, well, not that they're inherently flawed, but there are some things with standard analysis that we do, like volumetric analysis on cluster levels, that can be improved. So the classical cluster extend analysis is basically the most widespread analysis until now, I guess. So in the early days of fMRI, most of the analysis, most of the images that you see are all, you see brains, you see some blobs of activation, and these blobs are interpreted in terms of where they're located in the brain. And then we say, well, this task that we did activated regions in this area, and this most likely, this area does this sort of processing. And it goes, well, for everything. So what usually we do is we have this measured signal in the brain, in the voxels, that you might all be familiar with, I guess. And we do this inference on each voxel separately, right? So as opposed to using a very fancy spatial model, what we do is we take this individual region, this voxel, we calculate, we have the time series, we have our model, when the stimulus were given, convolved with the hemodynamic response function, and we get an estimate of every different location in the brain. And this is usually what you see in the outcomes of these analyses, are these clusters of activation, and they're basically a conglomerate of Z values or T values or F values, whatever sort of the test statistic is that you like or that you calculated. And the goal, of course, of this fMRI inference is to decide for each of the voxel whether there is activation or not. And this can be activation between different conditions, so it could be the activation, either it could be activation between zero, so for a rest condition and a task condition. It could also be the contrast between two tasks, for example. It could also be a group difference. In essence, that really doesn't matter. It could be the difference between two groups, or whether the contrast between faces and houses, for example, is different in group A than in group B, right? So in essence, the statistic map that you get is the same. It's a map of statistic values, and we have to decide which of all these values that we get are significant, yes or no. And this is quite of a struggle maybe, because we have a lot of these images. In a standard MRI analysis, not even the most fancy ones, we have over 200,000 voxels that we test for activation for. And each time we test, of course, for activation, we allow a little uncertainty of whether our decision is the right one, right? This is our alpha level, our 95% confidence level, where we say, okay, we allow a little bit uncertainty in these estimates. So every time we decide, based on the test statistics that we find, whether this voxel is active, yes or no, we're not doing it completely certain, but we allow for some uncertainty that one of these voxels that we test are actually a false positive one. So when doing multiple tests, these chances of making a wrong decision, or a family of tests, increases dramatically. So if we test just one t-test, we have a 5% chance, hypothetically, of making a false positive decision. But if we have two voxels or three voxels, this chance increases quite dramatically. So if we have 200,000 voxels, the chances that we find a false positive voxel, at least one, are very, very high. So what we want to do, and this was the goal, of course, in many studies since the inception of MRI, is to how do we control what we call the family-wise error rate. So how do we control that the fact that we do a lot of tests, so our family is the entire brain of voxels, how do we control this rate so that the clusters that we find are not false positive clusters, so that the statements that we make are not based on some random noisy data, but are actually regions that are active during our task, yes or no? So let me show you an example of how this is tackled in the traditional sense in a way. So say that we have this map of activations. These are all the raw Z statistics for the activations. The red ones are positive ones, the blue ones are negative ones. We'll focus on the positive ones for now, so we're left with a map like this. So what we have is we have in total over 166,000 in-mask voxels, meaning we have 166,000 voxels where we want to test activations. And these are, what we see here are Z statistics, and they indicate whether a voxel is more active in the non-vocal condition than in the vocal condition. So the experiment that was done on this is that people were in the scanner and people were listening to sounds that were either non-vocal, so non-speech sounds, or sounds that looked or sounded a lot like vocal sounds. So there weren't actually words, but they resembled words in a way. And these two conditions, we subtracted the activation from it, and then we got this map. So what we want to do is test the null hypothesis for each voxel, that if it's the null hypothesis is there's no activation, and the alternative hypothesis is that there is activation. And now we have to decide, based on these raw Z statistics, which of these values are actually significant, which are noise, which are significant, which are true positives, and actually which are false positives. So one way to do it is to do Bonferroni correction, which is the easiest thing to do. But as you can see, you're not left with a lot of activation there. So what we do is, if we want to control the family-wise error rate over all voxels in the brain mask, we just divide our p-value that we want, so 0.05 or another one, divided by the number of voxels that we're testing, and then we get a p-value at which we can threshold this image. So on the left side you can see it's the same data, but in the red pixels are basically the pixels that remain as significant. These are in blue on the right side, and these are overlaid on the raw statistic maps, right? So from the data that we gather, from the Z statistics that we get, this is what remains if we do family-wise error correction. The thing is, it's not very powerful in the sense that the locations that we find, so the regions that we find are pretty small, but at least we can be pretty certain that activity is actually there. So here comes a little bit of a trade-off, because if we do this strict correction, we have what we call, well, a high spatial specificity in a way. We can be quite certain that the activations that we find, so the blue and the red regions, the red on the left and the blue on the right, are actually there, because we controlled across all the voxels that we tested. We know that these are not, we almost certainly know that these are not false positive. And therefore, we can make statements about where the activation is. So we have high, what is called spatial specificity. And that means that we can be certain that if we look up what region is actually active, so what anatomical region of what part of the cortex is actually active, we can make a pretty good statement about this, is that in this task, this is the activation that, well, was there. But usually we are not interested in these single voxels per se, but we are interested in clusters of voxels, right? If we go one slide back and we want to interpret the regions that we find, we tend to interpret the regions that are somewhat larger, and the small regions we might discard, or we might not put much emphasis on in a way, because usually we expect that the activation comes in the sort of blobs of in a sort of blob shape. So in order to make a method that is somewhat more powerful, instead of doing this Bonferroni correction, what we can also control is the family-wise error rate, not of all the voxels, but of the clusters or the blobs that we find. So a cluster or a blob we define as a contiguous or connected set of voxels, right? So here you can see in blue, if we do a if we threshold the data at a relatively low level and we see what remains, we see that the blue blobs of activation remain. So what we control then, our family of is not all the voxels, but it's the set of blobs that we find. So we control the number of false positive blobs. So if we do an analysis, and what is called a cluster extend analysis, what we do is we control the amount of blobs that we find with our alpha level. So we know that the blobs that we find are not false positives. So in practice, this works by a two-step approach. So we choose a cluster forming threshold Z, and we estimate the size of all contiguous clusters above this threshold, And we determine the minimum cluster size k that occurs by chance under the null given the smoothness of the data and the chosen threshold. This is quite a long sentence, but it actually means that we have to decide on a cluster that should not occur by chance. So you can imagine that if we do an analysis that if there is a false positive activation, we can see one voxel somewhere popping up around, we're not going to trust that. We most likely say that's noise, right? If there are two voxels connected, so next to each other, the chances of that are already smaller than just one voxel popping up. But for example, if you find 100 voxels to be connected to each other, the chances of finding a blob of 100 connected voxels by chance is much smaller than just finding one single voxel. So this is the idea of sort of this cluster extend analysis, is that this is much more powerful in the sense that we can find these clusters. So what we do is we determine a value based on, it could be random field theory, it could be based on permutation. We find a value k, at which all clusters that have a size larger than k will be significant, and all clusters that are smaller than k, so smaller than the number of voxels, are deemed non-significant. And then if we do this, and I've plotted it here for different thresholds, so if we take a low threshold, like z is 2.3, then our k value is 597 voxels, and the blue regions that you see on the left side, let me see if I can get the pointer to work, that's over here. You can see we can find a lot of blue activation, a large number of clusters remain at this Z threshold, right? So for a higher Z threshold, so the threshold is somewhat higher, the K is 160, and you find some smaller regions, but you can still find some regions. If you set the Z value even higher, your K is 25, you can see the region becomes smaller. And actually, if we put the Z value very high, our K is 1, meaning that we're back at voxel-wise inference in a way. So the thing is that we have to decide beforehand which threshold to use. And this is a problem if you don't know your data, and you cannot choose it afterwards. You have to choose it before seeing the data. And then you have to decide on a Z threshold, and then you have to, well, basically stick with it. And of course, you could say, but, well, it's not allowed in a way to say, I see, for example, with this threshold, I see that my data is way too blobby. I find too large activations. I'll just put my threshold somewhat higher, and then I'll stick with this. It's a bit fishy in a way, because there is no formal way of deciding which threshold is actually the correct ones. All these analyses are perfectly fine separately, but they're not fine if you look at them first, then decide on a different threshold, and then do the analysis over and over again. So this can become quite problematic. And there's another caveat, and that is that this approach is really nice, but it is more powerful than the voxel-wise approach in terms of how many regions or how big the regions are that you find, but it is more powerful in detecting it, but not necessarily in localizing activation. And this is a bit of a problem, and this is because the hypothesis testing is on the cluster level. So the family-wise error correction is on the level of the clusters. So when we say there's no significance when the cluster extent is smaller than k and significant when cluster extent is larger than k, there is no information about how many voxels within a cluster are actually significant, yes or no, or are actually active. So the only thing we can say basically is that there is at least one voxel in the area that we find that is significant, right? So the test is actually there's no activation within a cluster, that's H0. The alternative hypothesis is there's at least one active voxel within a cluster. So the paradoxical thing is that the larger the cluster you find, the less you know about where activation is in a cluster. And this is what is called the spatial specificity paradox. It has been talked about, well, already I think 10 years ago, but it's not very common that everyone truly sees it every time that this is actually going on. So what we actually tend to do is when we see a cluster of activation is that we want to say all the voxels in this cluster are active. This is the way how many people interpret this. All the voxels in this cluster are active. They're surviving the thresholding. I have set my cluster threshold, I find a cluster, I can see where the overlap in the anatomical regions is, so I can make a statement about this. But this is what we actually cannot say. So we can say there's at least one voxel in the cluster that is active, but we cannot say that the entire cluster is active. And the paradoxical thing is, of course, that the smaller the clusters that you find, the more certain you are where it is in this sense. So if you find a cluster of just one voxel, you're certain that it's there. If you find a cluster of 500 voxels, you're not certain where the signal is. So the only thing you can say is at least one voxel in this cluster is active. That's not to say that there are not more voxels in the cluster active. It could be that all the voxels in the cluster are active, but the test that we do does not guarantee this sort of statement that we can make. So the only statement we can make is at least one voxel is active, but of course in reality it could be that everything is active, but we just don't know. The test doesn't say this. So this spatial specificity paradox can be phrased as a sort of trade-off between detection power and spatial specificity. So, as said, the statement, there's at least one voxel active, could mean that all voxels in the cluster are active, or it could be just one, we just don't know it. And the intuition is, of course, that there are usually more than one voxel active, right? Finding a cluster of 500 voxels, you wouldn't expect that to be driven by just one active voxel. But the thing is, we just don't know with the hypothesis tests that we do. So what we do, and this is what's going to be the topic of the next session, is we use what is called true discovery proportion-based methods to give us an in-depth analysis of what clusters are made of. And this true discovery proportion is basically a method that provides a simultaneous confidence bound across all the possible clusters in the data that allows us to drill down into clusters to see how much activation there is. So the true discovery proportion is, and let me just quickly show you or talk you through what it is without going into much detail. It's a multiple testing correction method based on closed testing. The closed testing method allows us to what we call make a simultaneous confidence bound, and that is a confidence bound that allows us to look into every possible subcluster in the data without losing family-wise error control across the clusters that we test. And this simultaneous bound allows us to estimate the number of truly active voxels within a cluster for all possible clusters as many times a researcher wants. So we can define the clusters beforehand. We can define the clusters after we see the data. We can change the clusters while we're doing analysis. We can do a Z threshold for one cluster and not for another. And still we have full family-wise error rate control over the activation, over the number of clusters in the activation that are significant. So this sounds a bit too good to be true in a way, and it's not. And it's, of course, if you give a talk like this without providing the proper proof of that it's not, but if you come by and I can show you why we think we can do this. And of course there's a sort of power trade-off in a way, because we have to calculate the simultaneous confidence bound, so that means that it's not as powerful maybe as sort of cluster extent thresholding, but for that change of power you get a lot of flexibility. So how does these TDPs look? So we can have a true discovery proportion. It runs from 0 to 1. And I've shown you here from 0.1 to 0.9. If we run the analysis and we estimate sort of, we set the threshold to find us clusters which have a true discovery proportion of 1, we can see that these are all the voxels that we find. So of all the voxels that are here, what we can say is that of this entire map, at least 10% of voxels are active within this cluster. So this is a pretty large cluster, right? You can see that the entire brain sort of almost lights up, and we can say that from this entire part, almost 10%, or at least 10% sort of is active. So we can up the threshold, so we can look at voxels which have a true discovery proportion of above 0.2, 0.3, 0.4, 0.5, and you see that the clusters become smaller and smaller, even close to the range of sort of being voxel-wise active. So a true discovery proportion of 1 means basically that we have voxel-wise accuracy. Of course, these statements of the very high TDP allow us to pinpoint explicitly where the signal is. And these TDPs that are very low, they have low spatial resolution, right? We cannot pinpoint where the activity is. The only statement we can make about this is that it's approximately 10% or at least 10% of the voxels within these regions are active, but we don't know where they are. So we do a statement on sort of the number of truly active voxels, so the proportion, but we cannot localize anything. So the funny thing, or at least I find it interesting, is that these true discovery proportion methods and cluster extent thresholding, sort of, the true discovery proportion allows it to explicitly say, make the spatial specificity paradox explicit, right? So what we can do is we can quantify the trade-off. So the true discovery proportion can be used as a value. Let's say if I want to be very certain where my activity is, I want a very high true discovery proportion. I might want to set it to 1, but then you're just doing voxel-wise analysis, but you can set it also somewhat lower. If your goal is just to detect if there's some activation somewhere, you can set a very low true discovery proportion, and it will give you some results. So it will give you a very large map, maybe with clusters. The only thing is that if you find a true discovery proportion of 10%, the only thing you can say is, well, we know that at least 10% of the voxels in the cluster are active, but we don't know where they are. So you lose some spatial specificity, but you gain some power in detecting the activation. So this is actually what is happening with cluster extent thresholding as well, by setting these different thresholds. The only thing is that here we cannot make it explicit how many voxels are active. We don't know how many voxels are active here. We don't know how many are there. The only thing is that the true discovery proportion allows us to do this. So we can calculate the true discovery proportion for every cluster in the data that we have, directly sort of stating how certain we can be that activation is already there. And these true discovery proportions, they allow us, well, basically to freely explore the data and freely go through all the clusters and provide true discovery proportions for every cluster that we find. So in this session, we will go over 3 approaches based on true discovery proportion. So Lucas will start and show our interactive applications how to explore these clusters of activation in the brain. And then Xu will show 2 TDP approaches in MATLAB. One is completely compatible with RFT thresholding, and the other one is the SIMS-based implementation, right? No. It's all the cluster-based. Yes. Okay. Strike that last sentence, but she will explain it to you. And finally, I will show an extension of Threshold Free Cluster Enhancement, which is a method often used in standard cluster thresholding. All right, so we also have some posters, but we'll put them on Slack, and we'll go over that later. I think we'll each mention them. So for now, I will give the floor to Lucas then. Yeah? The eerste. Ja, ja. This one. Ja. Okay, maar je moet daarna nog schakelen, hè? Oké.
Right. Hi, everyone. So I'll show you the software that we developed to do the TDP analysis. It's an interactive package. You can download it from GitHub. You can follow along, or you can just watch as I go through it. So it is available on, wait, oh. It's not my computer. What happens? How do I get back? Yeah, no. Back to the presentation. doet hij dit bijvoorbeeld?
Ja, dat doe ik.
So we made this very nice software package, but this is very difficult. There's some. Why is it not on the? But now it's mirrored and it's not coming to the. I think you need to put it extended. Daar, extend. En hoe vloog die naar de zijkant? Oh, dat moet ik uitkijken. Okay, sorry. Or you can just watch me go through it, because I'm going to show the whole thing. Yeah, so it is macOS compatible for sure. It's also Windows compatible, but it's still in the pre-testing stages. But at least the computational parts and the results are on point for Windows. Yeah, so there's demo data if you're interested. So that's it. Why? Next slide. Oh, okay. Then we need to switch. Ik had je toch leden. I'm going to do it like this. That will give presenter view? No, that's fine. Yes. Okay. All right, so just a few words before I show the toolbox. So what it does, it solves the spatial specificity paradox, as just explained by Wouter, using the all resolutions inferences. The computations are done in C++, and we combine that with a Python-based interface. So with the software, with the interface, you can interactively test and adapt any clusters that you find in your data or subclusters while maintaining that strict control, this family-wise error rate. It features real-time 3D rendering of a brain, and it superimposes your data on top of this. There are dynamic map overlays that you will see updated as you change the thresholds. And we have anatomical atlas integration running in the background, so you kind of know where, you get an idea of what anatomical region you are finding your results in. So it's a small disclaimer, it's the first beta version. We worked really hard the last year, but it means that there might still be some bugs in it. So if you start to use it and something is not working, please contact us. But any feedback on bugs, warnings, and your user experience is more than welcome. So the key features is basically what I just said. It does all of that, and it's built with Python, the front end. The back end is in C++. And yeah, it's ready for download on GitHub. So let's see if I can quickly go there. So here we have the GitHub page. It features the installation, so it's made very easy. In the end, all you have to have is a few packages. If you run this command in your terminal, it will set up the environment. It's a virtual environment that will basically try to put everything there and the package, and it's ready for use. So let's then use it. So what we do, once it's installed, you launch it from a terminal. And the very first time that you launch it, it takes a while. The second time and onward, it's much faster. So the first thing we get to see is two choices, whether we want to start a new project or if we want to load a previous project. And since we're all new to this, we'll start with a new project. We load our data. So it's a statistical map. Normally, the software will try to determine what the file type is, but sometimes this information is not in the header, and then it will notify you that you have to select it manually, and you can then select a background, a template to which you want to project your results on. Can be the raw data, so it would project the results of the clustering back onto the own data on the raw data image, or you can choose a template. So we can go for a template, so it's an MNI space then. And before I press next, what will happen now is, so because once I press next, we will jump right into the analysis. It will do a pre-computation part. It's basically the largest body of the computation. Basically, it's creating the solution space. So it builds a complete hierarchical tree of all the voxels in the brain, linking them together based on some settings that we have preset, but that you can change. And then it calculates the TDP for every single potential cluster within that hierarchy. And as a first result, it creates a gradient map. That's the first thing you will see by allocating each voxel with the highest TDP value of any cluster that it belongs to. So that's right away. So it's doing that now. So now it's communicating through Cython, which is a bridge between Python and C++, and it's communicating with C++, the backend. It's doing all the computations, and it's sending that information back to the front end. And that's the longest that it takes. And so that's the gradient map that I was speaking of before. So there's a lot going on, and before I start interacting with the data, I just want to explain a little bit how it's set up. So here on the left side, we have this column, so to speak. It features the statistical image, your data that is loaded. Currently, it's the Z-map that we just loaded. You have the opportunity to add more and run analyses on these, and then toggle between the different data maps. Here are the templates, so you can choose different templates as they are pre-installed in the package. You can also add your own, and you can simply also project it on its own background data, so that would look like this. Let's stick with this one, and it allows you to load atlases that will tell you the location you're at the crosshair position. Okay, so here we have the fully functional orthogonal view, as you can see. So it's not entirely, okay. Yeah, so normally you should see this, so there's some scaling issue here. But it will tell you the region you're pointing at. It gives some basic information here. The orthogonal controls can be changed, the transparency, and here you have your MNI coordinates, and you can simply change if you want to look for a specific region, and it will go there directly. Okay, so that's all great. So yeah, we have this 3D cluster viewer. It becomes more important once we do a cluster analysis. So here I want to point your attention to where you start to interact with your data, in fact. There's 3 tabs. You have the whole brain TDP. That's where we set a threshold, and we basically threshold the gradient map that you see here. The results will arrive in the cluster statistics, so the cluster analysis tab. There will be a table with all kinds of information, and there is a save, load, and export tab. So here we set our threshold. We feature the TDP-based thresholds and Z-score-based thresholds, and the other 2 are still in the pipeline. With the Z-score-based threshold, what you do is basically you set a threshold. The clusters that survive, the software will then try to determine the TDP value of those clusters. Here you set that threshold, so you can change it either with the slider or in the added box. So maybe you say, okay, I want a TDP threshold of 0.80. You hit return or run, and it will do the computations. So all those clusters have a TDP value of at least 0.8. And the results are then updated in the cluster analysis tab. And now you can inspect your results. And so you can either go through it, and you can select clusters through different means. You can select a cluster like this. It will be selected here. It will be shown in the table and here on your 3D viewer. You can get a sense of what it looks like. It's a bit difficult sometimes to interact with it. You can enlarge it if you want to see it more closely. And the table is also responsive, so you can click through it and inspect the different clusters this way. Now, importantly, you might want to change the TDP threshold of a single cluster and either enlarge it or shrink it. So we have a selected cluster here, which then is featured in the cluster workstation. So it's cluster 27. It has a unique identification number. We see the size in voxels, the TDP value, the z-score, etc. And then by interacting with this slider or this text box, you can change the TDP threshold of this particular cluster. So we can maybe crank it up to 90.95. It will do the computations, and you see that it shrank and it moved up into the table. There's a message log, so that's the way we try to communicate with the user. It can also be enlarged in case you want to see it a bit more up close. And as I said, you can add other data at the same time. So we can, for instance, add the same data again. It will prompt you to give the specification. It will again go into this first analysis. It will present you the gradient map. And this time around, instead of doing a TDP-based thresholding, we can maybe decide to do a more standard Z-based thresholding and then compare the results sort of side by side. So we would, again, we go for Z-based. We pick a Z-score, maybe of 5. We run it. Then it makes this clustering, and then it will go into the clusters and determine the TDP values of those clusters, which are now found here. And for instance, you can then toggle back between the first one and see how the results are different. And of course, you can add any number of maps. And then that's just one thing. You kind of don't need to change it if you just use it for the first time, but here you can change the analysis settings, like what the connectivity criteria and significance level, how we test, and whether it's two-sided or one-sided. Importantly, we also want you to save your project, load a project, and export your results. So that would be the end of the workflow in a way. So let's quickly do that. Where do we do that? Well, we can do it here. Okay, then it's quick. That's an older one, but it's the same one. So it will what it will spit out, what it will download to your computer is the different tables in CSV that you can use for like any way you like it. There is a report. It will export the Nifty files of the different cluster maps that you've created, and there is a convenient full report HTML that you can navigate to, which basically explains you, okay, these were the analysis settings, this is what you're seeing, here are the tables, and you can then go through them, and along with the tables, it will provide a screenshot of the clusters that you found with your analyses. And just very quickly, that's how you can use the software. And that is what I wanted to present you.
Sorry. So hello everyone. So in the following session, I'm going to introduce the enhanced cluster inference via cross testing for the true discovery proportion analysis. So first of all, I'm going to briefly recap what's the standard or the classic cluster inference. So the standard cluster inference allows you to do the family-wise error rate correction as what is introduced by Wouter in the previous session, and which is based on the random field theory. First of all, you need to make sure certain assumptions are satisfied. The most important assumptions include that the statistic image should be is assumed to be a stationary Gaussian random field, and this image is sufficiently smooth. When these assumptions are fulfilled, then we will be able to use the random field theory to make the two-step inference that was introduced by Wouter. So first of all, we need to specify a cluster defining threshold, like the Z threshold, and then we will be able to compute a cluster extent threshold K using this inequality. So if this inequality holds, that means the family-wise error rate is always under control. So when we define a cluster defining threshold, we will be able to find the K value. If we increase the cluster defining threshold, then we will be able to find the lower K value as what was introduced by Wouter. Then we will be able to make the further statement that if the cluster size is greater or equal to the K value, which is obtained by using this inequality, and then the cluster size, then this cluster is claimed to be significant based on the standard cluster inference. So our approach is based upon this standard cluster inference. So we will be able to embedding the cluster standard cluster inference within the closed testing framework. So first of all, we will be able to reproduce the same results as what we got from the standard cluster inference. And the second step is that we will be able to provide more information about the activation. So we will be able to provide the quantification of the activation using the so-called true discovery proportion. So it's essentially the proportion for each cluster, the proportion of the truly activated voxels inside this cluster. So which is equivalent to finding the number of the truly activated voxels inside this cluster. We have also proven that finding the estimate for the truly activated voxels inside a cluster is essentially equivalent to solving a K-separated problem in graph theory. So what is a K-separated problem in graph theory? So given a graph of vertices and edges defined using the connectivity criterion, so it can work for the 2D or 3D data. So for the 3D data, here we have an image of voxels and the connection defined using the connectivity criterion. We have phase connectivity, and we have the edge connectivity, and also the vertex connectivity. So the K-separated problem solving this K-separated problem is essentially finding a minimum size separator such that after removing this separator, all the remaining connected components will have the size at most k-1. So that means all the remaining clusters will be insignificant for this case. So we would like to find a separator such that removing that separator, we will have all the remaining clusters being insignificant. However, solving this k-separator problem in graph theory is an NP-hard problem. That means there's no easy solution for this kind of problem. When we are dealing with a very large cluster, then the computation time will increase dramatically. So next, I'm going to show you two different ways to approach the optimal solution of this k-separator problem. So the first one is called cluster TDP, and this is based on an exact algorithm using the techniques of tiling and pruning. And so using cluster TDP, we are going to approach the optimal solution of this k-separator problem from the lower direction. So this cluster TDP tool tends to give you a conservative and estimate of the TDP, and it will become like very small, particularly for the small or irregularly shaped clusters. However, this algorithm is non-iterative, so it can run really fast. And more importantly, using this algorithm, you will be able to control the fMRI's error rate all the time. So how can you run this cluster TDP tool? So first of all, please visit the GitHub repository webpage to download this SPM extension and then launch MATLAB. Then the next step is to add the SPM12 and cluster TDP SPM tool to your MATLAB search path using the following comments, and then you are ready to go. So So I'm going to illustrate how to run this. Sorry. First of all, I'm going to introduce the general usage of this cluster TDP tool. So this is the main function you would like to use to run this cluster TDP analysis. So SPM cluster TDP is the function with two optional inputs. So the first input will be this thresholded SPM structure, and the second one will be the character string specifying the CSV export for the summary table, like what you got from the standard SPM analysis. And using all these outputs, if you would like to explore the results in an interactive way, then you need to output all of these outputs. Otherwise, you will not be, you are not needed to output anything. So I'm going to show you how it works with the. Is it large enough? Maybe I should. Okay, I think it's large enough. So I'm going to show you first, if you don't want to do the interactive exploration, you can simply run this function name directly, so SPM cluster TDP, and if you press enter, then you would first require to select the spm.m file. So this is the spm.m file based on the dataset Wouter used. So this is vocal versus non-vocal contrast. So here we selected the vocal versus non-vocal contrast, and then we click done. Then we also need to specify the thresholding as what you did for the in SPM. So now we select the cluster defining threshold of 0.001 and the extent threshold being 10. So this is the nearly the same summary table as what you got from the SPM. The only difference is this column where we show the TDP lower bound using the cluster DDP algorithm. So if you have a closer look at the FWER corrected p-value, then you will be able to find this cluster is significant, and this one as well, and also this one. And the corresponding TDP for these three significant clusters are non-zero, while for the rest insignificant clusters, they have 0 TDP. So we will only observe non-zero TDP for those significant clusters based on the standard cluster inference. And if you would like to do the interactive exploration, then you would need to output all these 4 outputs, then run this the same analysis again by selecting first the SBM.mat file and then the contrast. And you need to specify the thresholding as what we did just now. Now we got the same results, but we will be able to move our pointer, for example, to this cluster, and then we select current cluster, then the summary table, the result table will be updated accordingly. And when we would like to show, for example, for the results for this cluster, then we just move the pointer over there, and then we click current cluster again, then the results will be updated as well. If we would like to go back to the original whole brain analysis results, then we could click this button, then the summary table is going to be updated as well. But please do pay attention to the intermediate output here, because for SPM, normally, given one cluster defining threshold, the minimum significant cluster size or the cluster size threshold will not be outputted. But here, we output this minimum significant cluster size, and which is going to be used in the coming algorithm that I am going to introduce. So the second algorithm that I am going to introduce is called the TDP clusters. So this is based on an approximate 2-phase algorithm. So the first phase is to find the initial clustering using a heuristic algorithm aiming to minimize the separator size. So the first phase gives you a suboptimal solution to the k-separator problem. And in the second phase, we optimize the clustering upon this suboptimal solution to find the global optimal solution of this k-separator problem. However, this algorithm is iterative, so it may not always converge to the global minimum within a limited running time. But compared with the cluster TDP algorithm, the TDP clusters tends to give you a more accurate estimate of the TDP, so we recommend you to run this analysis as well. So how to install this tool? So first of all, you will need to go to the GitHub repository webpage and download the standalone tool. Here, we build this TDP clusters as a standalone tool instead of the SPM extension, because running this algorithm in MATLAB is super slow. So instead, we run this algorithm in C and Python instead to enable a faster implementation. After download this standalone tool, you will need to open the terminal and navigate to the tools directory, and then run the following commands. So the first line is to navigate to the upper bound subfolder, and then you need to run make to compile this f3d function. Then you're ready to run the analysis using TDP clusters. So this is a general syntax that you might want to use for running this TDP clusters algorithm. So you will need to use this fgreedy function, and there are like different parameters you need to specify. The first one is the configuration file specifying the parameters and rules essential for this algorithm. And the second parameter is the global time limit in seconds. And the third one is the is n, which stands for the time limit, and which if there's no improvement within this time limit, then the algorithm is going to stop. We have already suggested the recommended value for these two parameters, and also we would like to recommend you always enable the use of this configuration file. So that means the first portion of this function, for this first portion, we suggest you to fix as it is, because all these parameters and rules are set based on running thousands of statistic image from the neural database. So what you need to specify is the K parameter. So the K parameter here is the minimum significant cluster size -1. So as I mentioned, the minimum significant cluster size is outputted in the cluster TDP. It is one of the intermediate output of the cluster TDP tool, and you need to grab that information which will be used here. And also the file. So here, for running these TDP clusters, you are going to run the analysis for each significant cluster separately, and the input file here will correspond to one cluster only, and each input file will save the XYZ voxel coordinates for each of the clusters, and which is saved in the CSV or TSV file. I have prepared one file that you will be able to use to generate this input file. Let's have a look at how it's implemented. So first of all, we need to grab this K value. So the K value is the minimum significant cluster size -1. So here, for this data set, that's essentially 129 -1. And we will be able to use this write cluster files, M file, to generate the input file for your TDP clusters analysis. So first of all, you will need to specify the cluster defining threshold or the cluster forming threshold. So you can change this based on your need. You could start with like 0.001. And you also need to update the K value, which is associated with the, your selected cluster defining threshold. And then you will be able to run this analysis, to run this command to generate the CSV files. So for this data set, you will find 3 significant clusters as what we shown previously. So finally, you will have 3 different cluster files generated based on this, this file. So what you could do next, you will need to run the analysis using the fGreedy function. And as what I suggested, please keep the first portion being fixed. So always use the configuration file and set -t equals 0 and -n equals 60. And then you would need to specify the K value, or if the K value is saved inside the file name, it will be automatically extracted by the algorithm. So you don't need to specify the K value here. I think it would take around like 3 minutes to run the analysis. So if you have a look at these results that I ran previously, So what's the most important information is this minimum score. So the minimum score represents the number of minimum size of this separator from this K-separator problem, so which stands for the minimum number of truly significant clusters or truly activated clusters inside this cluster of interest. So here, this cluster has a size 329. So what we need to do is to use this 52 over the over size 329, then that's going to be the TDP threshold that you are going to get for running this TDP clusters algorithm. So comparing these two algorithms, so for cluster TDP, we try to approach the optimal solution of the K-separator problem from the lower direction, so it tends to give you a more conservative results or more conservative TDP estimates, while for TDP clusters, it tends to approach the optimal solution of the K-separator problem from the upper direction. So generally, it will give you a more accurate results by providing a tighter bound. However, using TDP clusters, there could be the convergence problem, so the results might not always be valid. So we suggest you run the analysis using both tools and output the results from both tools. And this is an example that you could use for reporting your results by running this analysis. So first of all, please report the cluster defining threshold that you chose. So here we use 0.001, and also please output the corresponding cluster extent threshold based on the random field theory. So here we got 129, and for each of these three significant clusters, please report both the conservative bound and the approximate bound for each of these clusters. Then in addition to rejection or not, we will be able to give a more detailed interpretation of the activation for each of these significant clusters. So we have two poster sessions. We have two posters, 1049 and 1050, and we have the poster session tomorrow and the day after tomorrow. Please feel free to join us by then. And for more technical derivation of these two algorithms, you can refer to this paper. And for downloading this write cluster files, you will be able to follow this link and visit this GitHub repository to find this file, and also find a slightly more detailed handout for installing and running these two tools. Okay, thank you very much.
All right, so as the final part of this session about true discovery proportions, I want to talk about something slightly different in a way, but it's a nice extension of the closed testing principle for sort of standard cluster extent analysis, and that is what we call localized cluster enhancement, which is an extension of Threshold Free Cluster Enhancement, TFCE. That might be a method that you might know. And this, basically improves our spatial awareness of this method. So to start with, the Threshold Free Cluster Enhancement, the TFCE, uses basically neighboring voxels to support or enhance what we call support to enhanced clusters found after thresholding, right? With standard extent thresholding, we set a threshold at a certain level. Say we have found this one's working. We set it at a certain level, and the extent that we find basically defines how large a cluster is. So this is a slice of a cluster. Here we have all the, well, you can say it as a sort of 2D slice that we take. This is the height of the signal, and these are sort of all the voxels. And here you can see one of the hills that are there. So these, if you set it at the threshold here, you will see this hill as a sort of activation blob, this hill as an activation blob, and this one is gone, right? Isn't there? So setting the threshold mainly depends on how many clusters you find. If you set a high threshold, you find low activation, little peaks, but with a high statistics value. If you set a low value, you find more blobs of activation, but you. So the idea and the thing that I talked about in the first sort of talk was that the setting of the threshold is sort of arbitrary in a way. And threshold free cluster enhancement basically helps us setting the threshold. The idea was that the threshold, well, that's the threshold free thing in a way, is that it enhances sort of the cluster so that we don't have to define a cluster forming threshold beforehand. What this method does, to show you, is that it basically, for every voxel that we have, it calculates, well, or it enhances the cluster, or it enhances the value of the voxel based on the support that it has. So this might seem a bit weird in a way, but what it basically does is that we have a voxel here, and we want to calculate sort of an enhanced statistic value. So what we do, this enhanced statistic value is the integral of basically all the pink areas that we have here. So it's the sum of all the pink areas here. So this voxel here has a t-value, and the enhanced t-value will basically not be this value, but it will be the value of the sum of the entire, well, support as we call it. And this support is driven by two parameters basically. We have a height parameter, so that is the height that we have. For example, in the red, we have a certain height of this. And at that certain height, this blob where this voxel belongs to has a certain extent. And this extent, well, gives us basically the amount of signal that is here to add up. So it adds up everything from a low threshold, this is H naught, and it adds up everything below that until sort of this reaches the maximum value, and then sort of it adds up and it adds up and it adds up. So for every value that we have here, we have an extent and we have a height value. So this is H very close to 0. The extent is very large, so you have H to the power of H, capital H, and we have the extent of the support, and then everything is added up. So the thing is that we end up with this, well, this voxel, and we do this for every voxel separately, so that it gets enhanced by the support it belongs to, basically. So it looks down at the underlying structure, and it takes this into account. So what we then do is we do use permutations to calculate a TFCE significance statistic. So when we can calculate this for every voxel. And what we do is we calculate under the null hypothesis. So for example, between two groups, we permute the group labels. And we calculate TFCE statistics for each of the permutations. And we calculate the maximum TFCE statistic that way under the null hypothesis. And that way we can threshold the original TFCE map. So we know which TFCE value is can be regarded as significant or not. It's somewhat computationally intensive, but once you have the permutations done, you have a very nice sort of picture of this activations. So what it does, and basically what we see in many studies, is that if we do standard cluster thresholding or we do threshold-free cluster enhancement, that the clusters look much nicer when we do TFC. So if we look at, for example, this is the HCP data where we had 20 participants in the social contrast, what we see is that we have these clusters of activation over here. and all these regions of activations. And these are the significant TFCE clusters. So this is thresholded at the TFCE value calculated by the permutations. These areas remain as being significant. So this way you could be able to claim that there's activation there. If we now plot in darker blue the support of these clusters, you can see that there's a lot of information in the brain being used to support these clusters, right? So this is basically at the lower sort of threshold. So the blue ones are actually all the voxels that are used to provide information, to provide the support for these TFCE-based clusters. And the problem is that the same thing that holds for standard cluster extent thresholding holds for TFCE still, is that if you find a cluster, you don't know exactly where the activation in the cluster is. You just know that there's at least one cluster, at least one voxel in the cluster significant. So localization is not very good if you find large clusters. And for TFCE, the problem is that this statement goes for all the voxels that make up the support as well. So instead of having a spatial problem where at least one voxel in this cluster is active, and these are the regions that we now have to make that statement on are much larger. So the spatial specificity of TFCE is even worse than for standard sort of thresholding. And this is a bit of an issue if you want to make statements about where activation in the brain is. And for this, we more or less provide a solution. So this is some simulated data where we simulated a 2D map, and the yellow area is just signal. It's a bit of a weird shape because it's square or rectangular. It's not round. If we add some noise to it and we smooth it, we can get some data for t-statistic. And then if we calculate the TFCE statistic, this is what it looks like. So this is the general thing that you see in TFCE light data, is that you see the t-statistic is sort of pretty much all over the place, and you see some blobs of activation. And what you see for the TFCE statistics is that the blobs that are really sort of high, they get enhanced a bit, they get somewhat higher, and all these low things are sort of suppressed in the data. So it enhances the clusters that you have, and it suppresses the smaller ones who don't have a lot of support. So if you would threshold the TFCE statistic based on permutations, you would get an area like this, with the dark blue, again, the support. So the weird thing, and that is what TFCE sort of picks up, is that there is now a region also here that seems to be significant according to the TFCE statistic. And I'll come back to these two later on, but this is what we find, and in this case we does even find a false positive cluster where we would say that there's activation, while there is actually not. So the thing with TFCE is then that it doesn't have very good error rate control. So on the left side, I've shown you the cluster error rate. So this is the error rate of finding a false positive cluster. And there we can see that cluster extent thresholding, so the standard thresholding method, properly controls the false positive rate, which is over here. So this is the number of clusters across the number of clusters, and this is the error rate. And what we see here is that TFCE has much higher cluster error rate. So it doesn't really control the cluster error. Both methods do not control the voxel error rate, but this is what we already determined in that, if you can see from the previous slide, the cluster extent thresholding, the standard method, does sort of a good job in detecting the overall sort of cluster, but it does detect some voxels, and it misses some voxels here that should be there, right? So it does detect some voxels that are actually not there. So on a voxel level, it doesn't control properly, but at least sort of cluster extent detects one cluster, and threshold free cluster enhancement in this case selects two clusters. So this is why TFCE in this case has less cluster error control than cluster extent thresholding, but both have not very good voxel error control. Right. So what we try to do is improve the TFCE statistic using the closed testing procedure. So the closed testing procedure is the statistical framework that underlies the true discovery proportion estimation as well. And what it does, it provides a p-value for each region that is tested. So in this case, the threshold TFCE map can be used as a mask, and you can test to see whether whether this region is what we call localized cluster enhanced significant. So the LCE outcome, based on the localized cluster enhancement procedure, shows us that this is the actual cluster that we find, but not this cluster, right? And this is the same shape as the threshold of TFCE image, but for these two clusters that we find, only LCE says this one is significant and not this one. So it's a sort of add-on to sort of threshold free cluster enhancement. It's different than sort of the TDP analysis in that sense, is that we don't provide a true discovery proportion for this area. So the statement is still there's at least one active voxel in this region, but at least what it does is it has the advantages of TFCE in that it can improve sort of the cluster, that it uses the information around the clusters to sort of make the clusters or enhance the clusters. So it uses the spatial information around it. But it doesn't have the problem that it sort of finds too many false positives. So it kind of solves the problem that we have too many false positives, because the support of TFCE is taken into account when sort of doing these analyses. So it's a sort of add-on, as you could say. You can do it after sort of your TFCE analysis to give you some extra information of whether whether the clusters that you find are actually significant. And the nice thing about this is that you can use it on any cluster basically that you have in the data. So you can use it on any cluster that you define also afterwards. You can get TFCE or LCE significant statements on, and I'll show you an example in a bit. So the way it works, without going into formulas, is basically we start with the TFCE statistic for all the voxels, which is this map. These are the TFCE statistic, and we mask out a region of interest. So as said, this can be any region that we have. So it can be sort of the TFCE thresholded map. It can also be another map. For example, this is from the middle frontal gyrus, I guess, that we just masked out. And that we just take as our mask of interest. And we can use as many sort of regions that we want. We can do that indefinitely in a way. And we use the TFCE procedure basically on only the masked data. So we take the TFCE statistic, we mask them out, and we redo or calculate the local TFCE statistic to calculate LCE significance. We're working on the paper at the moment where we have this all written down. But this is the general idea. So we use TFCE, we mask out a region, we take the data from that region, and we perform TFCE on the masked data to get sort of the value that we need to define whether this cluster is significant, yes or no. And because it is in a closed testing procedure, we can do this indefinitely for any cluster that we have. So, as said, I've gone over this a little bit in a way. In this case, we've taken sort of the mask in the light blue as our clusters of interest. Basically, there are two ones, this one and this smaller one, and we calculated the localized cluster enhancement procedure. And in this case, this is the only one that remains. So these light blue regions were the mask, and the LCE significance says this is a cluster that has at least sort of one active voxel, which is LCE significant. So based on the TFCE threshold, this is a cluster we can trust. Still, the thing is we cannot localize really if there's activation in this cluster other than there's at least one voxel active, but at least we have a consistent TFCE cluster interpretation, and we have a consistent way of sort of the LCE statistic is consistent with the TFCE output. So there are two things, and maybe I still have to go back to the slides a bit. There was one little thing that I haven't talked about, and I should, and that is that in the original TFCE implementation, the part or the point where we start to add sort of support for these voxels is what we call H0, and that is usually set to 0. So that means that all the statistic values that you take into account are taken into account when calculating the TFCE statistic. It's easy in this way, and this is why it's threshold free in a sense, is that because if you set H0, it's basically, you do that for every voxel. You don't have to define a threshold beforehand, but you just take 0 as a threshold. Well, this is where we have interesting discussions with people. You can say that it's threshold free in a sense because we take 0 as a starting value, but 0 in essence is also a threshold, of course. It's only a very low threshold. You could also do this method, TFCE and LCE, with a higher threshold. So you can set a threshold beforehand. And what we found is that it's usually more powerful to have a somewhat higher threshold. And it basically is because these support regions, basically the low T values, they're all taken into account into the statistic, but they don't really add much to the data, right? If you would set a threshold that is somewhat higher, the local support would be essentially much stronger in a way, which was kind of paradoxical when we found it. But of course, this introduces sort of the arbitrary threshold that you need to set, again, into the equation, but still it can pay off to have a threshold that is not 0 in a way. So to show this, we have here some results where we've taken a Harvard-Oxford atlas, and we use those as regions, so the different regions in the Harvard-Oxford atlas, to test for LCE significance, using a threshold of H0 is 0. And this shows you basically, for these masked regions, which of them were significant. So here's the significance level. These delineated sort of regions are the masks, basically, the cortical masks, and you can see that these regions are all significant, and these regions are not. And the rest of the regions in the mask, so the regions that you don't see, they were non-significant, right? So this is one of the nice things about this TFCE or this LCE statistic, is that you can do this after you do the TFCE analysis. You can provide the clusters that you want, and you can calculate the LCE statistic and basically get significance that way. So what happens when we use a higher threshold is that we see a lot more activity in the data. So if we set our H0 to be 3.1, so not 0, we do TFCE again, but now not integrating from H0, but integrating from H0 is 0, but integrating from H0 is 3.1. We get much higher LCE statistics. So there's one little caveat. You can adjust its value, but this value must be set before seeing the data. So the clusters you provide to the TFCE analysis are just fine. You can define them afterwards, beforehand, whatever you like. The only thing, you have to fix the TFCE analysis beforehand. So if you want to do a TFCE analysis with H0 is 0, that's fine. If you want to use H0 is 3.1, that's also fine, but this is, you have to pick one and you have to stick with it. But then you can test any region using LCE afterwards. That's the nice thing about it. So here you can see that actually sort of having this higher threshold kind of makes sense in a way, because you find sort of more evidence for activation in this one. And here are them next together. You can see that, well, basically the difference. There is a lot more regions that come into play. But of course, this is not allowed to do both, but for educational purposes, sometimes it is. All right. So in the last few minutes that I have, I wanted to quickly show you the implementation, because it's a MATLAB implementation, and it's relatively easy. The files can be found on the website as well. And the MATLAB implementation is made by Sam Davenport, who unfortunately couldn't be here at, oh, wait, I have to, yay, there you go. So I've gotten some example data as well. So it's a MATLAB implementation, and it runs the TFCE analysis for you, and it also then runs the LCE enhancement, and it's also pretty fast. So the first thing you do, we have an MLX file available at the, can I just make this bigger? Yeah, that makes it easier to read, right? You can download the StatBrains package, which is on the website, copy it into your directory, open MATLAB, and add the directory to the path. Switch to the StatBrains directory and add it to the path. You can run it. We have an example data set that we can use. I have to put a URL here. I will update it. And then we have to load the data set. So we can do that here. So you can switch to the correct directory and you load the 4D image. So basically what you load is in this case, we load 13 subjects, 3D images, and we concatenate them, to be one 4-dimensional file where the fourth dimension is the subject dimension in a way. And we also need a mask. So we need the first mask to mask out the brain voxels in order for the analysis to run smoothly. After that, we have to set some parameters. And this is basically the same parameters that we need to set for the TDP analyses as well. We have the connectivity criterion, which is 18 or 26 most of the time. We have to set the H and the E parameters, which are set by default to 2 and 0.5, which are the default settings from the TFCE paper, which makes it makes sense to leave them at default. We haven't checked a lot into how they change the results, but there are some things there as well. Basically, they define how much weight you give to the height of a voxel and how much weight you give to the extent of a voxel. In the paper, we also talk about how we can tweak these parameters and the TFCE sort of formula to include we can do also cluster mass or peak analysis, basically on the height of the value. So you can tweak the analysis to be so that you can use them, for example, if you know that you have high small peaks, you can tweak the analysis a bit to search for that in a way. So you can treat that. The DH value should not be changed, which is just an internal value to how to approximate the integral. But the H0 parameter is more important because it defines the lower threshold of the TFCE support, as said. You can set it to 0 for this analysis. I've set it to 4.4. And then in this case, we perform a very simple one-sample t-test, basically looking for average activation across the contrast that we're interested in, to see whether there is an average activation across the 13 participants in a way. And we use the t-test for that. So it's relatively, I can run it all, and then you can see how it works in a bit. So all these functions are provided in the StatsBrain package, so you can just make the t-statistic, mask it out with the MNI mask that we have. And then we can calculate the TFT statistic. So this is the TFT statistic for the t-stats image. You provide the right parameters to it, and then it will run. And then if we've made this TFCE map, we provide that to the permutation procedure, which provides you with the TFCE maximum statistic so that you can threshold the map. And after you threshold the map, you have to provide, we can calculate the TFCE significant clusters that are left, and we can provide these, in essence, to the LCE procedure, and the LCE procedure will give you p-values for each of the clusters that we find. So if you run it, and we run everything, then it will start doing things. We get a progress bar, so this is the permutations. Normally it doesn't go that fast. I've downsampled the resolution a little bit to make it somewhat faster for now. But at least you can see that it's nicely progressing in a way. Usually it takes about 2-3 minutes, depending a little bit on the amount of subjects that you have and the size of your maps that you provide. And this is the step that takes basically the most time. And the nice thing about the LCE procedure is that it can use these permutations later on to calculate the statistic without having to do the permutations every time over and over again. So these are progressing. Then the LCE procedure is running, the progress is already there. And then what we have is we basically have 8 regions, and we have 8 p-values to go with it. And some of the p-values are significant and some are not. And that's basically what you get in addition to a standard analysis, is that you get these sort of extra regions of activation. Well, to quickly show you, this is always on the different, quickly show you the difference between the two analyses. I've opened up sort of the blue areas are the LCE significant statistics, and the red ones is the TFCE statistics. So there we can see that the TFCE method would provide, well, the blue regions basically that you see, these are significant according to TFCE, the red ones, sorry, and the LCE ones, the remaining blue ones are the ones that are actually LCE significant. So for example, for this region that we have here, we wouldn't say that there's enough evidence for any signal in there. So we would basically say that these were false positive regions and that the blue regions are the TFCE significant regions. So these maps are outputted and can be used in any further, for any further exploration. And I think that is about it for this. So this concludes sort of the TDP session. We'll have a short break. We'll start at, quickly speaking at my schedule, we'll start at 4:40 again, so in 20 minutes. And we'll have Tom Mullen speaking about spatial uncertainty and confidence regions. And then thanks and see you in a bit.